Good afternoon, students. This is your makeup video for September 28th. And in this video, we're going to be looking at Kepler's first law. You will need your notebook and a Chromebook. Basically, we're going to be taking notes for most of this class period. And so your homework or your finished product for this will be to make sure that your notes are finished, and there will be one either calculation or problem that you'll be doing at the end. We are going to be working on learning targets 1, 2, and 3. So those are all having to do with Kepler's first law and describing the orbits of different celestial objects and predicting the orbits of different celestial objects through the use of Kepler's laws. So the first thing that we're going to do very quickly is to set up our notebooks. So I'm going to pull this over on the screen so that you can see it. You're going to go to your next free page and you're going to label this Unit 2 space. You can go ahead and continue numbering if you wish. Then you can add in a table of contents. Make sure that you're pausing the video as you go so that you can fill in what you need to, but I'm going to go pretty quickly so that we get a pretty short video here. So next is your table of contents, page number, title or subject of the day, learning target numbers, and the date. I'm using as an example last year's notebook, so you can see obviously we weren't in the middle of coronavirus, so we had a little bit different dates, but your first dates to go in would be 9/28 if you want to put in your glossary, and Kepler's law also is on 9/28. Your glossary will look like this. You put in your glossary, term, definition, and then a section for prove I know it. When I'm doing this on my own, I usually draw in lines that divide this way. That is up to you whether you want to do that or not. So that's the notebook setup that you need to do for the beginning of this unit. Now, I'm going to leave a little bit of space here, and I'm going to go ahead and show you how to set up your notebook. We're going to do Cornell notes as a kind of as a usual thing as we go through our notebook. So we're going to go through these notes here in just a little bit. But what I do for Cornell notes, this side of my page over here is where I can put in headers. It's where I can put in various notes to myself that you can see down here at the bottom. It's where I could put in questions that I might wonder, and then I can go back and find those pretty easily. So the way that I set this apart is I fold my paper, and then I can draw a line down through there. On a lot of my pages, you'll see that I just have the fold and I don't go back and draw a line. You can do whichever one you would like. So I'm going to hop off of this for just a second. We'll come back and forth between what I want to show you for my notes and the Space Systems PowerPoint that you have access to. So we're going to start off by looking over here at the PowerPoint. You can access this from Google Classroom. It is available to you in Google Classroom. So we're going to be working with space. Specifically, we're going to be looking at Kepler's first law, which is the law of eccentricity. And if you're thinking about the word eccentricity, you might think of the word eccentric, which would be kind of a deviation or a change from normal. So that's a little bit of what we're going to work with here. We're going to work with a standard, and we're going to see how these different orbits might deviate from that standard. We are working in the HS-ESS1-4 standard, where we are using mathematical or computational representations to predict the motion of orbiting objects in the solar system. So for this one in particular, we're going to be working on the orbits and talking about how round or how elliptical orbits are. So we'll get to that in just a couple of seconds here. As we're getting ready to start this unit, there are 3 of Kepler's laws. We're going to tackle the first one today, but there are 3 laws from Kepler. So the first one is the law of ellipses, and that says the path of the planets about the sun is elliptical in shape, with the center of the sun being located at one focus. The second one, law of equal areas. An imaginary line drawn from the center of the sun to the center of the planet will sweep out equal areas in equal intervals of time. I call this the pizza pie law. Everybody gets the same amount of pizza, even if the slices of pizza don't quite look the same. We'll talk more about that in the Tuesday video. And then the third law, which we'll talk about later this week, is the law of harmonies. The ratio of the squares of the periods of any two planets is equal to the ratio of the cubes of their average distances from the sun. We may be listening to some harmonies as we go through this particular law, because this is the one that I think is the most math intense and might be the one that gives us the most headaches. So maybe we'll put a few harmonies in while you're listening or while you're working on this so that you can listen and soothe your brain just a bit. Okay. Moving on. Let's go ahead and dive in here to the law of ellipses. Now, you are welcome to go through the rest of this video as we work. You are welcome to continue to look at these slides. I am at this point, though, going to switch back over to my notebook because you can see maybe a little bit more of a condensed version of what the notes might be as I've written them out. So I'm going to switch over to my notebook. You still have all of these slides if you want to use them on your own. So let me exit out of this and let me go back here. And here we go. So when we are looking at this information here, when we are looking at Kepler's first law, when I'm writing my notes, I'm going to put Kepler's first law up here. This is in the blank little maybe quarter space of the sheet. This is my first title. And then I'm going to start my information over here. I've put the date up here. Again, these I'm using last year's notes. It's the same thing. I'm just not writing them over again. So you would put 928 up here for the date. So planets orbit the sun in paths called ellipses. The sun is going to be found at one focus, and there's going to be an imaginary point at the other. You'll want to write, this is what your notes will look like as well. I'm going to move through these. Feel free to pause as you need to. An ellipse is more or less an oval, but it's a special kind of oval. It doesn't look like an egg. It looks, it's more even on each side, and it has a special mathematical definition. So it is a special curve in which the sum of the distances from every point on the curve to two other points is a constant. And you can look at that here. So here are the two foci or foci. These are the two focuses, which is not actually the right word. And here is the orbit. So if we're talking about the sun being at one focus, the sun might be here. This is the imaginary focus, and the orbit of the planet would be around like this. And we'll see later why that's important and how this all fits together so that we can predict planetary motion. Okay, here are the parts of an orbit. There are the two foci. This in red right here is the distance between them, and we call that distance F. From this point right here in green all the way over to this point right here in green, this is called the major axis. The length of the major axis is d, lowercase d. So lowercase f, lowercase d. Just in case you are curious about this, this dotted line is called the minor axis. That's the shorter axis. We're not actually working with that. That's just that's free. No charge for that information. So let's take a look at what these words mean. So a focus is one of two stationary points in the center of the ellipse. One of the foci will be the celestial object around which the body orbits. The other one will be imaginary. The focal distance or the distance between the foci, is called f. We just went through this. Here you can see it again. The major axis is the distance across the long portion of the ellipse, goes through the foci, and we call that lowercase d. It's important for us to know that information because we're going to use those two distances to come up with a ratio. That ratio is going to tell us the orbital eccentricity. It's going to tell us whether or not our planet or our celestial body orbits in a perfectly circular way, or if it is eccentric, if it moves away from that. So let's take a look at what this might mean. The uh, the formula that we use here is E equals F over D. And so we know that this is the distance between the foci for F. We know that the D is the length of the major axis. And so this is a ratio. So the eccentricity is the ratio of the distance between the foci to the major axis length. All right. And we just have that written out over here. Ratio, I put little shiny things out from it so that you can see, oh, this is important. All right. As we move on down through here, we can do some calculations with this. So this is where we start to worry about or involve the calculations and the computations. So now we're going to look at that. Here's the calculations part. This is another way that we could write out our formula. The eccentricity, the orbital eccentricity, is the focal distance, F, divided by the major axis distance, D. Here, I've written out the steps that you'll need to follow. Identify the variables, write out the equation, fill in the equation, and remember to include units. So F is equal to 3.2 astronomical units. D is equal to 7.1 astronomical units. So this is doing step one. This is identifying the variables. This is a really simple equation. And so you might say, oh, I don't know that I need to do this. However, we're going to move into some much more complex calculations tomorrow. So I would like for you to pay attention to what these steps are. Okay. So 2, write the equation. This is just to make sure that you have the equation correct and that you then substitute in the correct values. So we know that F is 3.2 astronomical units. So we're going to write that in here, 3.2 astronomical units. We know that D is 7.1 astronomical units. So we're going to write that in on the bottom. That's our substitution, 7.1 astronomical units. So now we have done step number 3. We filled in the equation and we're ready to solve the problem. 3.2 divided by 7.1 gives us 0.45. AU divided by AU cancels out. It essentially gives you 1. Like x divided by x gives you 1. Same thing here. So the units, AU divided by the units, AU gives you 1. Those cancel out. You can just kind of stop writing them here. And it's a ratio, so there shouldn't be any units in a ratio. So this tells us what the orbital eccentricity is. But what does that mean? What does that mean for, like, okay, 0.45? Great, wonderful. I have no idea what that means. I can get a number. What does it mean? Okay, let's move on to the next page here. You may or may not be on the next page. And let's go ahead and let's figure out, well, what does that mean? Again, I have a new page, so I'm folding my paper, folding it back. If you want, you can draw a line down through here, but this is where I will continue to make my headings, and this is where I can write any questions that I might have. So this is a great way to interact with your notes. So let's consider what happens if you have two foci on top of each other. If you've got two foci on top of each other, what's the distance between them? It's 0. It would be 0 AU. There's no distance between them. They're right on top of each other. So in this case, I'm going to tell you that the eccentricity is 0. That would be my claim. Well, why is that? If F is 0, it's not going to matter what the size of the major axis length is. Because anytime you have a 0, it doesn't matter what you divide it by, you're always going to get 0. And that's our reasoning. So this is kind of like our claim. our evidence, and then our reasoning. Because if we look at the eccentricity is equal to the distance between the foci divided by the major axis length. If we have f equals 0, 0 divided by anything is 0. Now, here is where you might find a mistake, and it's something that I see pretty much every year. I always have a couple of students who tell me that 0 divided by anything is 0. Think about that. Is that true? Sorry, that anything divided by 0 is 0. I just said it backward. Is it true that anything divided by 0 is 0? Can you divide by 0? No, you cannot. You cannot divide by 0. So please make sure that you are saying that 0 divided by anything is 0. Okay? So this is how we know the eccentricity of a perfectly circular orbit. The eccentricity of a perfectly circular orbit is 0. So anything that has an eccentricity that is close to 0 is going to be very close to a circle. Anything that has an eccentricity that's a long way away from 0, that's closer to 1, is going to have a much more eccentric orbit. It's going to be much flatter. And that's what we're going to go into with our last part here. I'm going to cover this bottom part up. I probably should have earlier, if that's okay. You are going to work on this on your own. So what I would like for you to do is to compare eccentricities. And if you're following along in your slides, you can see that we've worked through the 3 problems that are at the end of the slides. So I'm going to give you a checklist, and I want you to work on this on your own. So I want you to compare the eccentricities of the 2 planets that are given in your third calculation at the end of your slides. And what I want you to include is the formula. I want you to discuss the ratio, and I want you to make sure that you're referencing 0, which is a perfect circle. So this is your checklist. Now, this is the first time that you're looking at any of this, so I fully expect that as you're going through this, you're going to run into some issues along the way. That's fine. I want you to give it a try. I've talked super, super fast. Feel free to back this up, go back through different parts of it, look at it again, come into class with questions. If you're watching this because you are in quarantine or you're off for an extended period of time, please feel free to email me. If I have several students who need some assistance with this, then we can figure out a time, if you're offline, that we can set up a Google Meet and do some offline help session as well. So hope you're doing well, and I'll see you in class or I'll see you online.